be here, and let me tell you, you're in for a treat, because my friends, it's time to start talking about Newton's 3 laws of motion. And I gotta say, the fact that they're so simplistic, yet they explain pretty much all low velocity type motion, it's just unbelievable that he came up with it when he did, and it's just stood the test of time. So let's get right into it. We'll start with Newton's first law. And Newton's first law states that an object at rest will remain at rest, and an object at motion will remain in motion unless acted upon by an outside unbalanced force. It's something that you're going to need to memorize verbatim, word for word. So don't just try and paraphrase it. This is how I want it to be memorized. And why? Because it's amazing what this says. It says if something's going to sit there, it'll never move. And if something's moving, it's not going to stop unless something else gets in the way and makes it stop. Another way to talk about this is this idea of the law of inertia. And the definition of inertia is that there's this tendency of an object to remain at a constant velocity. So you have all felt the effects of inertia before, and let's give you an example. Let's say you're racing around a track on a go-kart, and I actually had students in my class last year that had never been on a go-kart, and I hope you're not one of them, because there's 3 times when you notice your particular inertia. The first one is when you're stopping. Think about it. You're rushing at a velocity, and then you slam the brakes, and what happens? You physically want to move forward when the cart is slowing down. Why is that? Because your body wants to continue moving forward, but the seat belt or the steering wheel or your force on the steering wheel is causing you to stay with the carts to actually slow down with it. So there's a prime example. The second one is turning. Think about when you go around a corner at a very high speed. What's happening? You actually want to continue to go straight, so you end up leaning away from the curve for a little bit before you realize you're doing the turn. Then you'll actually drop your shoulder and lean into it. Your body wanted to continue along its straight path. It doesn't want to go on a curve. So that's why you felt this sudden force pulling you towards the corner. And that's a whole idea of circular motion, which we will deal with in grade 12. The third one, much like stopping, is this idea of starting. What happens when you accelerate a car very, very fast? You get sucked back in your seat. Why is that? Your body doesn't want to move. It wants to sit there, but the car is saying, nuh-uh, and it's going to push on your back, and it's going to push you forward hard, and you're going to actually suck back in. You're going to feel all of this force on you. It's quite an exciting experience. So these 3 ideas right there, just in go-karts alone, just show the majesty of Newton's first law in action. Now, when I say it's Newton's first law, there are arguments, and very fair arguments, that all the other laws apply as well. And that's absolutely true in a lot of cases. So never think that just because I'm talking about first law that I couldn't apply Newton's second and third law, which you don't know yet, but you will, into the situation. There's never necessarily just one law that applies. So let's get into another way of thinking about this. So in Newton's first law, you can also think about that there's no net force on the object, so it'll stay at a constant velocity. Now this is something that's rather new. So let's draw a picture to represent this for you. But first, I want to state that if it's not moving, then it has a constant velocity of 0. So if it's not moving, okay? Now there's going to be situations where there will be no net force on an object, and it will be moving. We'll get into that when we get into dealing with the calculations involved with dynamics. But for now, constant velocity of 0 if an object is not moving. Seems like common sense, but it's worth mentioning. So let's imagine this. A book is sitting on a table. There is a force of gravity pulling down on the book, but there's also a supporting normal force pushing up on the book. The way I like to talk about this is the book falling through the table? And the answer is no, it's not, which means there has to be some force pushing back up on it. And what we're going to do is show you a side view of this. So there's our pretty little table, and there's our book right there. Now, there are 2 forces acting on this. What I'm going to draw is something called a free body diagram, which we're going to do a whole lesson on in the future, so don't panic about that. And if we take a look at the center of our object, we have the force of gravity pushing straight down on it, right? Pointing towards the center of the Earth. But it's not actually falling through the table, which means the table is pushing up on the table with another force which we call the normal force, which is labeled as F sub n. So this is a free body diagram, a little more intricate than what you're going to need to do, but this gets the idea across. Now, if the force of gravity was larger than the normal force, what's going to happen? That book's going to break right through that table. So in this case, nothing's moving. What is its velocity? 0. And just to reiterate it, it does stay at rest with a constant velocity of 0 because the forces are equal and balanced, right? So it's pushing as hard up as it is down. Therefore, there is no net force. These vectors will, in fact, cancel out. Let's take a look at one more example. In this case, if I drop a book from 2 meters, there is only a downwards gravitational force acting on it. Now that the forces on it are unbalanced, what does the book do? Well, let's draw the same picture again. Now I'm just dropping it in free space. And when I let go, what's the only force on it? Well, the force of gravity. There is nothing pushing up on it at this time, so what's going to happen? It's unbalanced. It's going to move in the direction of the unbalanced force. So in this case, it's going to fall towards the floor. Now, there's a couple of you probably that are like, well, wait a second, there's air resistance and stuff like that. Notice the distance that I'm dropping it from. At a 2 meter distance, air resistance is essentially negligible for a large book. Now, you can talk about the idea of dropping a piece of paper versus a bald piece of paper. You can talk about skydivers and stuff like that, but there are other variables involved there. We're just talking about a good old-fashioned textbook. When we drop it from 2 meters, there's insufficient time for air resistance to have any significant impact on this. So what's going to happen? It's going to accelerate. Okay? So, this is Newton's first law. Object at rest will remain at rest, and object at motion will remain in motion unless acted upon by an outside unbalanced force. There's your unbalanced force right there. So, that's the beginning. If you're working on my worksheets, you've got some other examples of Newton's first law. You're going to be getting a conceptual worksheet to deal with Newton's first law a little more theoretically. But get ready, my friends, because next class we are going to deal with a whole bunch of math with Newton's second law. So good luck. We'll talk to you again.